All right.
We're golden.
Thank you very much. So we'll make this a longer lecture. I need to cover the remaining 3 arithmetic functions. I did not discuss them at all in class. And also maybe review an example of each of the type of problems we already discussed in class. So maybe I review those quickly. Wilson's theorem and Euler's theorem. Fermat theorem, we can jump over it because it's already included in Euler. So a quick example with Wilson's theorem, and then a quick example with Euler's theorem. Especially since, as I mentioned earlier today in class, there's a more elegant way to solve the problem. So for Wilson, and I'm also talking to those who maybe missed several of our lectures, so they don't know Wilson's theorem. Wilson's theorem, P is the prime. I don't need to write the full statement. For any prime, P minus 1 factorial is congruent to minus 1 mod P. A typical problem, for instance, is if we have something similar. So let's say find smallest integer and say larger or equal to 50, for which n is congruent to 19 factorial mod 23. 23 is a prime. We are tempted to immediately use Wilson's theorem. In this case, we know that 22 factorial is congruent to minus 1 mod 23. But our number n is not congruent to 22 factorial, so we want to construct 22 factorial out of this congruence. So I start with the given congruence, then it's congruent to 19. We'll do this quickly. 19 factorial mod 23. Multiply both sides in such a way to create a factorial, to create specifically a 22 factorial on the right side. I'm thinking, what do I need to multiply the right side to get 22 factorial by 20, 21, and 22. So this is congruent to 20 times 21 times 22 times our n. So again, n is congruent to 19 factorial, and then I multiply by 20, 21, 22, and I get the full 22 factorial. And that's congruent to minus 1 by Wilson's theorem. So at the same time, to make this quick, 20 is congruent to negative 3, 21 is congruent to negative 2, and 22 is congruent to negative 1. So we get minus 3, that's 20, or minus 3 is congruent to 20, times minus 2 times minus 1 times n. It's congruent to, this is congruent to what I have on the line above, to the product, 20, 21, 22 times n. And it's congruent to 22 factorial, which we know by Wilson's theorem, it's minus 1. Congruent to minus 1 mod 23. Multiplying these small numbers, I get minus times minus times minus. It's a minus 6. And congruent to minus 1 mod 23. I automatically, without thinking, just multiply by minus 1 to get rid of these minuses. And I get 6n congruent to 1 mod 23. I would like to keep the statement of the problem on the board. So I jump from here. I don't know if we can I? I think it's visible if I write it small. Yes, it looks like it is.
Yeah, so we can move it.
Okay, so 6n congruent to 1. it means that n is the inverse of 6 modulo 23. But the easiest thing to do, instead of thinking about should I use Euclidean algorithm to find the inverse, as we know, we discussed that we can do. No, the fastest thing is just to replace 1 by another number that's congruent to 1 mod 23, and a number that is automatically, or that is already a multiple of 6. So I write 6n congruent, and I can put anything in place of this one. 1 plus 23 plus another 23 and so on. 1 plus 23 is already 24. That's good. It's divisible by 6. It's congruent to 24 mod 23. Now I can cancel the 6 because 6 is relatively prime with 23. 23 was a prime number, so no problem. Dividing the congruence by 6, I get n congruent to 4 mod 23. If I didn't make any mistake, yes. N is congruent to 4. If you see I make any mistake, interrupt me immediately. Yes. Now, what is the answer to the problem? Is the smallest number larger than 50? That's congruent to 4. So this congruence has solutions, say solutions to the congruence lots of solutions. 4 itself, 4 minus 20, 4 minus 23 should be negative 19. Smaller numbers. Plus 23 is 27. That's not good enough. We want an n larger than 50 plus another 23. I just made this up. And it is exactly 50. The next plus 23 is 50. And then the next one is 73 and so on. So now I need to go back and look at the statement of the problem carefully to see was strictly larger than 50 or larger than or equal to 50. Let's see how we got it. Larger than or equal to 50. So 50 is allowed. So our answer is 50. 50. That's an example of quick example of typical application of Wilson's theorem. Now, let's discuss an example where we want to find the last 3 digits of a number. We discussed this earlier in class today, but I wanted to present another method which appears to me to be just a little bit more elegant. Of course, the other one works. And especially if we go through the Euclidean algorithm and we are allowed to use calculators or things like this, then of course we can do that quickly. But this is in some sense elegant. I want to show that. With exactly that problem that we started to work on and that I didn't finish in class. Number was 1, 2, 3, 4, 5, 6, 7 to the 799 or whatever. Last 3 digits. And now the number is a large number. To the 799. Whether it's 799 or it was 1599, it's the same thing. And actually the same last 3 digits. Because this comes down to finding the inverse in all these cases. Because it's 1 less than a multiple of 400. So we start by doing exactly the same thing. We say we work mod 1000. We work mod 1000 because we want to find the last 3 digits. If the problem asks us to find the last 2 digits, we can work modulo 100. We can still work modulo 1000 and the answer it will give us 3 digits, but it's more work for no reason if we only need the last 2 digits. If we need the last 4 digits, then we need to work modulo 10,000. So word mod 1000, a given number here, 1, 2, 3, 5, 6, 7, not the product, but 1,234,567 is congruent to 567 modulo 1000. You raise both sides to this power, and I get that the given number to the 799. It's congruent to 567 to the 799. Mod 1000. Regardless what the problem is, we can always replace this number by a smaller number, not by a smaller number, but a number less than 1,000 by using these constants. We can still have a large number in the exponent. So now we use Euler's theorem. We already did in class. Euler function computed at 1,000, 400. We did this. I don't need to. Or maybe I should review this for those who may miss the class today and want to have a look at the video. For any number n, I can compute Euler function as follows. It's the number times a product. We write a symbol like this. Product of expressions of this form. 1 minus 1 over p. For all those primes p, the product is over all those primes p, so p is a prime. Not all the primes in the world, but just those that divide n, that are divisors. Over p divides n. In our case, if we go back here, how do I see that this is 400? I'm going to erase this 400 and compute it by our general formula. We just need to know the general formula. It's 1,000. And then there are only two prime numbers that divide 1,000. One is 2, the other is 5. 1 minus 1 over 2, 1 minus 1 over 5. And this, it's 1,000 times 1 minus a half is 1/2. 1 minus 1/5 is 4/5. When I multiply these numbers, 2 times 5 is 10, 1,000 divided by 10 is 100, times 4, 400. As we computed earlier and as we claimed. So this is 400. With this additional piece of information, we come back and state Euler's theorem in this case. By Euler. Euler's theorem. Our number of interest, it's 567. It's raised to a large power. This number, what we know now by Euler's theorem is that if we raise this to this other, where we put the exponent to be 400, there's the value of the Euler function at 1,000 is congruent to 1. So this to the 400 is congruent to 1 mod 1,000. In order to apply Euler's theorem, I needed the number 567 to be relatively prime with 1,000. I don't need to check this, but I should state it, especially if I take an example. Let's state it. 567 and 1,000, the greatest common divisor is 1. And this allows us to apply Euler's theorem. And allows us to conclude that 567 to the 400 is congruent to 1 mod 1,000. Next, I raised both sides to same power, something that's close to the given number. In this case, I just squared them. Oh, I think in class we did 1,500, and because I needed to raise to the 4th power. Was it? Or no, it was like this. Earlier today in the other recording when we tested.
Yeah, I think it is
1599. Okay.
Yeah,
Okay. In this case, it's 5 567 raised to the 799. It's very close to 800, very tempting for us to use Euler's theorem and to get this and square that, because it's very close to 799. And it's 567. Squaring this congruence to the 800, it's congruent to 1 mod 1000. But 567 itself is congruent to 567 to the 799. It's congruent to question mark mod 1000, a number. It's such a number that I want to find. It's a number with the following property, that if I multiply the number by 567, then I get 567 to the 799 times another 567 is exactly 567 to the 800. So this number, if I multiply by 567, I get a number that's congruent to 1 mod 1000. So this number that's missing here is exactly the inverse of 567. We discussed in class that one can use Euclidean algorithm. So this is congruent to x. I want to find x, but the idea is that if I multiply one more time by 567, I get, then the number is congruent to 1. So 567 times x is congruent to 1 mod 1000. How do I use Euclidean algorithm to compute this? We can use Euclidean algorithm as we did on our first hour exam to find a linear combination that looks like this: 567 other numbers, a linear combination times x plus 1000 times y equals, I still have, equals 1, equals the greatest common divisor. So we know that the greatest common divisor of these two numbers, 567 and 1000, is representable. One can find x and y to represent it like this. And then if I interpret this as a congruence, I can get immediately what I needed, because 567x minus 1 is equal then to minus 1000 times y. So it's a multiple of 1000. So the difference is a multiple of 1000. Just by definition of congruence, I get the congruence. 567 times x is congruent to 1 mod 1000. So that's exactly the x that we needed. Here. So I use Euclidean algorithm to solve this, find x and y. Then I ignore y. I didn't need it, but just the Euclidean algorithm that we know, it gives us both of them, an x and a y. I won't need the y, I just need the x, and this x is exactly the one that I needed here. I look at its digits. If I get x to have 3 digits only, those are the 3 digits I'm looking for. Now I want to show another method here, which is a bit more elegant, I think. It goes like this. I wanted to find the last 3 digits of this. So a good part of the proof is the same. Of course, it goes to Euler's theorem, to computing Euler's function at 1000, and so on. So I do this until I get this congruence. How do I do this? I start from the beginning, and that's my suggestion for an elegant solution. Find the last 3 digits. I don't know what the digits are. Let's denote them somehow. So that's the first novelty. Denote the last 3 digits of a given number by, I don't know, some letters. Let's say A, B, C. in this order from left to right. Then let's see. Then this number, it's a huge number. I don't know its digits, but I know the last 3 digits. Actually, these are the digits that I don't know and I need to find. But I know that I denoted them by A, B, and C. So it's some lots of digits, and then they end with an A, a B, and a C. They don't, they're not multiplying. These are the actual digits of the number. We saw that this number is congruent to 567 to 799. This was congruent, and we found that earlier. But the given number is congruent to 567 to the 799. So 567 to the 799, it's a somewhat smaller, I mean, it's much smaller number than this, but still huge. So it starts here. Lots and lots of digits. But the last 3 are still A, B, C. And one more thing we know, and this time from Euler's theorem, that 567 to the 800, it's a number, it's larger than this. It's obtained from this number by multiplying by 567. It's a bit larger. I know the last 3 digits. They are 001. Why? Because the number by Euler's theorem is congruent to 1, more than 1,000. So numbers that are congruent to 1 are 1, 1001, 2001, 3001, and so on. So numbers that end with 001. So if I look at this carefully, I need to find the numbers, these digits A, B, and C, such that when I take this number and I multiply by 567, then I get this number, and the last 3 digits are 001. So this translates to the following problem for us. Just a simple multiplication with unknown numbers. So that's elegant. So I have this large number that ends with A, B, C, and it's equal to 567 to the 799 is equal to this long number, and I multiply this by 567. I do the multiplication. No, I don't know. How do I do the multiplication? I think 7 times C. It's something. I don't know what the number is. 7 times B. I don't know any of this. Then I multiply by 6. I don't know the remaining of the digits. The rest of them I don't know. By 5 I multiply. I don't know. What I do know is that when I do the multiplication, I add these numbers up. I get a large number such that it's the last 3 digits are 0, 0, and 1. Because by multiplying the given number by 567, I get then the number 567 on this line to the 800. So that's equal to something that ends with a 001. Once we see this, we can erase everything else. And let's see if we can, without a lot of computation, we can derive what these digits are. It's a simple problem. I need to find 3 digits A, B, C. There is a unique solution. Such that when I multiply by 567, I make this multiplication, I get 001 as the last digits. Now, 7 times C it's something, but this something needs to be a 1. Because when I add them up, I need to have a 1 here. So this forces C to be 3. 7 times 3 is 21. Gives us a 1. 7 times anything else, any other digit, will be a different number, will not end with a 1. This already gives, so C is 3. Now that C is 3, I can say something else. I will erase this just to make, I want to make a mess of what I have on the board. I put C equals 3 here, and I redo this multiplication. So it will look like this. So I have A, B, and 3, C being 3, 5, 6, 7. I multiply them. I know a bit more now. I know that 7 times 3 is 21. I have a 1. I don't know what this is. I don't know what this is. But I know now what 6 times 3 is. It's 18. I have an 8 here. I also know what 5 times 3 is 15. I have a 5. Although I don't know other digits. I know this 8. I know this. So now I add these numbers. And I get, oh, I know what I should get. 0, 0, 1. Some other digits that I don't know. Now that I know that this has to be, so this is an 8, because this was a 3, 3 times 6. So now I know what this digit right here has to be in order to get a 0. In order to get a 0, I need to have a 1 in here, and I need to have a 2 in there. Because 2 plus 8 is going to be 10, and so a 0. Gives me a 0. Now I go back, and this tells me what B is. So B is equal to, let me think. I have 7 times 3 is 21 already. So B has to be 0. If B is not 0, is anything else, it will 7 times beats some other number that doesn't end with a 0, and I have to add that with this 2 coming from this multiplication. Good. Now that I know that B is, I know what B is, I start the multiplication again with this additional piece of information. So now I have an A, B now is 0, C, and C is 3, 5, 6, 7. You drop the phone?
No, my phone. For a charger.
It is okay?
Yeah, it's good.
So this, and I don't need to redo the whole thing. I just copy what I had before. So this is a 2, a 1, an 8, a 5. But it's easier for me to see. And for others who look at the video, it's going to be easier to see if I use it separate multiplications here. And this is 0, 0, 1. So now I have 1. 8 plus 2 is 10. Oh, before I do this, this number I should be able to, this digit I should be able to find. This is 7 times, because I know I have 7 times 3 is 18, and I have 6 times, 6 times 3 is 18, 6 times 0 is 0. 0 plus 1 is 1. It's an 18. So again, coming from 6 times 0, 3. So that's a 1. Now let's see what digit I need to have here in order to give me a 0. So I have a 1 here. 2 plus 8 is 10. Gives me a 1. Plus this 5 is 6, plus this 5 is, plus this 1 is 7. So this has to be a 3. So again, 3 plus 1 is 4, plus 5 is 9, but I have plus another 1 coming from 8 plus 2 is 10. Then it will give me another 0. So I found this number that's 3. And now I come back and I find 8. A equals, and then I give the answer. So the last 3 digits of the given number. 1, 2, 6, 7 to the 799 are from left to right. A, that we'll find A in a moment. B at 0 and C at 3. So A, comma, 0, comma, 3. These are the 3. Okay, it remains to find this A. So I have, oh yeah, it's very easy. I have 7 times A is something, but I have a 7 times 0 is 0. So it doesn't add anything here. 7 times A has to end with a 3. 7 times, and there's a unique solution. That's what we already know, it's a unique solution. So once you see what digit is, it's a unique digit. 7 times 9 is 63. So A is 9. And this becomes 903. And the and then I give the answer. If I had a calculator, I'll just multiply these two numbers. No, I don't want to erase, as we found. I would multiply these two numbers, 903 times 567, and I'll get a number times this, times 567 equals whatever it is. You'll see that it ends with a 001 as it should. Let me check. So I can do the multiplication just to check my answer. And if I see that it isn't, I don't cheat. I don't use a calculator to actually compute. I come back and do the reasoning and see what I made a mistake. But I don't think I made any mistake. Now that's an example with Euler. Euler's theorem, how we use this. Next, I need to talk about arithmetic functions in a certain order. Oh yes. Yes. Our other colleague who's coming to help. Erase the board. Please do come. He's recording what I'm saying. Yes. And as we promised earlier today in class, this lecture will be longer and we'll upload it later. It's longer because we want to make sure that I go over all the necessary theory and enough examples. Now we've seen enough examples with Wilson's theorem, with Fermat-Euler. Fermat's theorem is always containing Euler's theorem, so it's enough to use Euler's theorem all the time. So there are 3 arithmetic functions. Oh, and first of all, what is an arithmetic function? 3 arithmetic functions. We still need to talk about. Now let's see first what people mean by an arithmetic function. Any function that's defined on where the domain of definition is the set of positive integers or the set of natural numbers. It's called an arithmetic function, even if the function itself doesn't have any special properties. Good, so now they both left. Oh, I'm all alone. I hope that it's still recording. Let's go to the essential things. Very short, very simple. So, as an title for the chapter, let's say this is chapter 3. Arithmetic functions. The main definition is this. The definition. Arithmetic functions, or an arithmetic function is a function whose domain is the set of positive integers. Let me write. What's the function? Any function. It doesn't have to have any special properties in order for people to call this arithmetic function. Any function whose domain is a set of integers. So we can talk about if f is the given arithmetic function, we can talk about f of 1, f of 2, f of 3, not f of 1.5. It's not defined f of 1.5 because 1.5 is not an integer, not a positive integer, not an integer. Some functions that are defined on positive integers, like Euler function, as an example, have additional properties. And one of them, that appears many times in problems in number theory, is so-called multiplicative property or multiplicative function if the function has the property. So let's define the definition. An arithmetic function f is multiplicative, so is now the definition may be a bit surprising, so I go carefully over it. If f of m times m is equal to f of n times f of m. This is not surprising. This is what one would expect. Multiplicative function. The product is equal to f of this times f of that. What's surprising is that in this definition, people do not ask the property to hold true for all n and m, only for some of them. So whenever n and m are relatively prime. So what this means is that if a function satisfies this property, that f of n times n is equal to f of n times f of m for all m and n, for all pairs of numbers m and n that are relatively prime, so the greatest common divisor of n is 1, then we already call this an arithmetic function. Even if the property fails for some of the pairs n and m in case they are not relatively prime. In case this property holds true for all pairs n and m, then we say that the function is completely multiplicative. It's part of the definition. F is completely if what we expected initially from the definition, that f of n times m is always equal to f of n times f of n for all n. When you say for all n m, for all n m positive integers where the function is defined. Maybe we should see an example where the function is when a function is multiplicative and it's not completely multiplicative. Because if all the functions that are actually multiplicative are automatically completely multiplicative, then there's no point to define this in two different ways. the function we already discussed before is Euler function. And that function is an example of a function that's multiplicative but not completely multiplicative. Let's see. Let me actually complete. So we can state it as a theorem. Maybe it's, yeah, and it's, I think in our textbook it's stated as a theorem. The function is multiplicative. And it's theorem, I guess, 3.2, if I'm not mistaken. Euler phi function. Actually, we denote it like this Greek letter, right? Is multiplicative. One way to prove it, now that we have a formula for, we have a, in some sense, we have a better theorem that tells us exactly what Euler function is, because it's exactly the number times the product over all prime divisors of that expression, as we know. Gives us more information than just this theorem. It says the function is multiplicative. So in practice, we can just use that one. But from that one can immediately prove that this is multiplicative, and I don't go into the proof, it's immediate. However, I want to see an example. Let's say we computed earlier, and we found that this is 400. We computed Euler function at 100. And we found that it's 40. If anybody missed that lecture, you can do this immediately, because it's 100 times the product, same product, 1 minus 1 over 2, 1 minus 1 over 5, it gives us a 40. We computed this, found that it's 4. Suppose I compute some other, suppose I compute Euler function at 8. If I use our general formula, it's just a number times 1 minus 1 over. I take every single prime, divide it. 8 doesn't have, 8 has a single prime factor, that's 2, so it's 1 minus 1 over 2. And this is equal to 8 times 1 over 2, it's 4. I can see this directly from definition. So in case anybody missed the lecture when we define Euler function, by definition is you look at all the numbers up to n, in this particular case 3, 4, 5, 6, 7, 8, and you look at only at those numbers that are relatively prime with 8. So those are exactly the odd numbers. This 1, 3, 5, and 7. Half of them are even. And I count how many numbers relatively prime with 8. Then I have exactly 4. In general, for a prime power, we can do this by definition immediately. For instance, what is Euler function computed at 125? If I am to do it by definition, I would say it's 125. I count all the numbers from 1 to 125. I remove those that are divisible by 5. 125 is just 5 cubed. It doesn't have any other prime factors but 5. So numbers that are not relatively prime, those that need to be removed, like those that are even in this case, are those that are divisible by 5. Now in the first 125 numbers, how many are divisible by 5? In every 5 numbers, in every 5 consecutive numbers, I have one of them that's divisible by 5. So the total number of numbers divisible by 5, it's 125 divided by 5, that's 25. And this is, oh, that's 100. But again, if I allow myself to use the general formula, as I should, I don't have to worry about such things. I don't have to compute, to look at, to think about numbers relatively prime or not relatively prime. It's just to the number. I don't need to do it by definition. In other words, I can just use the general formula. So Euler function computed 125. It's the number times 1 minus 1 over 5. Because 5 is the only prime factor of the number. And this is 125 times 1 minus 1 over 5 is 4 over 5. 125 divided by 5 is 25 times 4 is 100. So no matter how we compute, again, of course, we get the same answer. Now, as an example of using this theorem, this will be the following. I can compute Euler, same thing that was computed earlier. I can compute Euler function at 1,000 by writing 1,000 as a product of two numbers that are relatively prime. I can write it as 8 times 25, 8 times 125. So 8 times 125. I can do this regardless what the function is because I didn't compute anything. I just wrote inside it. Before I compute this, I write 1,000 as 8 times 125. The two numbers are relatively prime. So now we use the theorem saying that the function is multiplicative. These two numbers are relatively prime, so it gives us this is equal to 8 times the function computed 125. These are actually the two values we computed. Euler function at 8 is 4, so this is equal now to, I don't know if it's still visible. I should write this. This is equal to 4, and this one is equal to 100. We computed it in two different ways. Euler function at 125 is 100. So indeed, when I multiply them, I get 4 times 100, I get 400. So if I want it, I can compute the Euler function in this way. Euler function at 1,000 is equal to its value at 8, and it times its value at 125, because the two numbers are relatively prime. However, if I try to do it this way, if I say, oh, 1,000 is also equal to 10 times 100, I'm getting the wrong answer. So indeed 1,000 is equal to 10 times 100. But the two numbers are not relatively prime. The theorem doesn't tell us that the function is completely multiplicative. If the function was completely multiplicative, I could write the value of the function, Euler function at 1,000 is equal to its value at 10 times its value at 100. Well, this is simply not true. This is 400. This number is 4, and this number is 40. Computed So 4 times 100, so 4 times 40, it's not 400. So this is not true in this case. And it shows, this is an example that shows that Euler function is not completely multiplicative, because there exists at least one example that we found where it doesn't work. So, and we can find plenty of others. So, Euler function is not completely multiplicative. That's one thing about this. An example of a function that is multiplicative, but it's not completely multiplicative. Funny thing happens, the remaining 3 arithmetic functions we need to study in this chapter are, and each one of them is in the same situation. Each one is multiplicative, but none of them is completely multiplicative. So let's proceed to discuss them one by one. The number of divisors. Now, before I do that, so if I have Euler function in a problem, best thing to do is to just use directly the formula that we know. Like for instance, when we work with, we want to find the last 2 digits of a number, at some point we need to compute the value of the Euler function at 1000. We just immediately computed using our general formula, found that it's 400. Of course, I can get that same answer by writing is as, okay, Euler function at 8 times Euler function at 125, but it's wasting a bit more time. Not much more time. So there are only 3 remaining functions, arithmetic functions of interest for us right now. So like in this video. And I'll take them in the same order as they are described in our textbook. Number of positive divisors. There's section 3.3. Positive divisors. Or the number of positive divisors function, as they write. To emphasize that it's a function, and we denote it like this. We just put as a definition or a notation. That is in the textbook. I'll just write it quickly. This is the number equals the number of divisors, but I only count the positive divisors, not the negative divisors. I mean, -5 is also a divisor of 1000, and -2 is also a divisor. We just count the positive divisors, and their number is denoted like this, the number of such numbers. So the number of positive divisors of n. That's an example. The number of positive divisors of 6 is 4, because there are 4 divisors of 6, 4 positive numbers that are divisors of 6. If I want in a problem to see them, okay, I'll write them down. 1, 2, 3, and 6. These are divisors of 6. another example if I want is number of divisors of, let's see, the number of divisors of 100. Number of divisors of 100 is, I don't have it here, but I guess it should be 9.
The formula powers of the prime factorization.
Exactly, that's exactly what I was thinking about, applying the formula. They will want to talk about it in a couple of minutes. Yes. Yeah, we'll talk about it in a moment, but let's see this just by definition. I'm saying this is 9, and to double check, I just list all the divisors of 100. 1, 2, 3, oops, already made a mistake. That's why I need some people to be here to correct me. The next one is 4.
2, 4, 10. 10, right?
10. Yeah, I can say 10.
25. 50.
25. 50.
No, there's more.
And 100 itself.
Yeah.
All right. So these are all the.
Not all. But,
1, 2, 3, 4, 5, 6, 7. They are not all.
yeah,
We're missing 2 of them. But let's see.
Yeah. 20.
20. Where is this 20?
Yeah.
I'll put the 20 in here.
0, 2, 5 squared.
So now we have no. Write this again with much larger letters.
Yeah.
You are in the video as well, but so that's visible because this is how we count actually.
Yeah.
Please do write.
Of course. Yeah. So
With large letters, so it's visible on the video.
0, and then 2 squared. Same thing. 4.
So 2 to the 0, that's 1.
That's like this the number of. We could just.
And then multiply them by, okay.
Yeah, and then
So we get 9. So let me see how we do this. First of all, I just want to write them in an order. I want to make another point here. It's useful sometimes. Divisors come in pairs. For each divisor, there's another divisor such that the product of the two is equal to the number. So, maybe I can use this while I list divisors. So I have a divisor that's 1. I already have in mind another one. That number times 1 is 100, and that's 100 itself. The next divisor is 2 here. So the previous one is 50. This is helpful sometimes. I don't need to check any number between 50 and 100. It cannot be a divisor of 100 because if it is, it's going to be 100 will be that number that's a divisor times something, but that something will be in between the 1 and 2. Impossible. Okay. The next one here is 4. And 4 times the corresponding divisor is 100. That's 25. So I got 6 divisors. The next one is 5. I don't know if I had it earlier. 5. And 5 corresponds, you can put it in pairs with 20. So that 1 times 100 is 100, 2 times 50 is 100, 4 times 25 is 100, and 5 times 20 is 100. So we put them in pairs, but there's one missing because we said that this is 9. So we're missing 1. But how can we miss 1? Because that 1 that's missing, we can put in pairs. The only way this can happen if the missing 1 is in fact in pair with itself. So in other words, if it's the square root of the number. So that's a good thing to keep in mind. Maybe not for our first exam, just for later. The number of divisors is even unless the number was a square. Because if the number is a square like 100, we can put them in pairs, except for the square root of the number that's still a divisor, 10 in this case. And all the others are in pairs. So that's why this is odd. If the number is not a square, the square root of the number is not an integer, so then we can put all the divisors in pairs. Like in this case, 1 and 6, 2 and 3. The product is 6, the product is 6. Okay. Now, what our colleague here said, it's a smarter way to count the divisors. If we look at powers, 2 to the 0, 2 to the 1, 2 squared, 5 to the 0, that's a 1, 5, and 5 squared. The reason we look at powers of 2 and the powers of 5 is because the given number was 100 and its prime factorization is the power of 2 times the power of 5. So what this tells us is, let's take a number in general and see what we can say about the number of divisors if we have the prime factorization. Again, now that you both are here, I just interrupt myself for a minute to ask the following question. Can you two talk to each other about your schedule for? You did?
Yeah.
Okay, you'll let me know later. Okay, just to make sure, because I'm available anytime. So, suppose we do this for 100 first, and then we see how this immediately generalizes, and it's a simple formula. So 100 is 2 squared times 5 squared. If I think about this, any divisor of 100, 7 is not a divisor, 33 is not a divisor, 3 is not a divisor. The only divisors are powers of 2 times powers of 5. But provided the power of 2 is not larger than 2 squared, like 8, 2 cubed. 8 is not a divisor of 100. 4 is, this is 2 squared, and 2 to the 1 and 2 to the 0. So that's why the only possible powers of 2 that I can have in a divisor are exactly as he said, 2 to the 0 or 2 to the 1 or 2 squared. The same for 5, just because I have a 5 squared in here. Possible powers of 5 in a divisor are 5 to the 0, that's 1, 5, and 5 squared. Now that I have this in mind, now I know that the total number of divisors is 9. That's the product here of the number of choices. So I have 3 choices for the power of 2, 3 choices for the power of 5. Or in other words, if you want, 3 choices for the power of 2. 1, 2, and 2 squared. 1 being 2 to the 0 and 2 being 2 to the 1. 3 choices for the powers of 5. 1, 5, 5 squared. And I can make quickly a table that has 9 elements that are all the divisors. 1 times 1 is 1, 1 times 2 is 2, 1 times 2 squared is 2 squared. That's our 4. 5 times 1 is 5, 5 squared. 2 times 5 is 2 times 5. 5 times 2 squared, I can write this 2 squared times 5. I can multiply them and see that these are exactly the divisors we had before. Like 2 times 5 is 10. 2 times 2 is 4, as I had before. 2 squared times 5 is 4 times 5 is 20. We had 20 before. Next one. 5 squared we had, it's 25. 2 times 5 squared. And then 2 squared times 5 squared. 2 times 5 squared, that's 2 times 25, that's 50. We had 50. And 2 squared times 5 squared, that's the given number, that's 100. But, so if I actually want to see the divisors, I can multiply them and I have the list in front of me. If I just want to count to see how many, this is a smarter way to count, because now I see that they have to be 9, even if I don't write them down. I have 1, 2, 2 squared, 1, 5, 5 squared. These are the only possibilities. Similarly, if I want, so the number of divisors is 9. Suppose I want to compute the number of divisors of 400. Question mark. More divisors. let's not write down all the possible cases. Let's just think for a second. First of all, I find the prime factorization of the number. 400. It's, I don't know, it's a 4 times 100. It's a 4 times 10 times 10. None of this is the prime factorization. It's just useful maybe for me. And this is, I have a 2 squared here, I have another 2. It's a 2 to the 4. Times I have a factor of 5, another factor of 5. I have 2 to the 4, 5 squared. I should have known this, because I knew that 100, it was done earlier. 100 is 2 squared times 5 squared. What's 400? It's just this previous number multiplied by 4. So a power of 2 changed from 2 squared to 2 to the 4. The power of 5. Exponent of 5 in the prime factorization is the same. So now let's just think. I have how many choices for divisors? Well, I still have 1, 5, or 5 squared as powers of 5. I cannot have higher powers of 5, but I have more powers of 2 available. I have 1, 2, 2 squared, 2 cubed, 2 to the 4. Then I can take any number in this column, any number in this row, multiply them and get the divisor. Different divisors. How many I have here? 3. How many I have here? 5 numbers. So the total number of divisors is 15. 15 divisors. I come back and I say this is 15. Now let's see. Are we ready to discover the general formula? It didn't matter that these were powers of 5. If we had, instead of 1, 5, 5 squared, if we had 1, 7, and 7 squared, it would be the same thing. Still 15 divisors, but they involve these 3 powers of 7 instead of these 3 powers of 5. So now we realize that it's not important what the primes are in the prime factorization, only what the exponents are. I have 2 to the 4, the largest possible divisor, but they start with a 2 to the 0, that's a 1. 1 is a divisor, so 2 to the 0, 1, 2, 3, 4. So that's why there are 5 of them, because they start with 2 to the 0 and with 2 to the 4, there are 5 of them. So this exponent plus 1. And this 3 is obtained exactly the same way. We had 1, 5, 5 squared, so there are 3 of them. The exponent is 2, the number is plus 1. So this gives us a general form. And the same here. This exponent plus 1 times this exponent plus 1 is 9. So let's write down the general theorem. Oh, before I write down the general formula, let's write this theorem that the function is multiplicative. But we don't use this. I mean, we use directly the general. We write this as a theorem. Function is multiplicative. Like for instance, this number, let me see, what was this number equal to before I compute? let's see, prime factorization. 400 was 2 to the 4 times 5 squared. That's what we had earlier. These two numbers are relatively prime. 2 to the 4, that's 16, and 5 squared, that's 25. So using this theorem, I get that, or if I just want to check the theorem in this particular case, I would have so nu of 400 is equal to nu of 16 times nu of 25. What is it? Let's check. What's this? Nu of 25. How many divisors does this number have? Well, the only divisors are 1, 5, and 5 squared. So 3 of them. And this, how many divisors we have for 16? We remember these are is 2 to the 4, and we realize it's 2 to the 0, 2 to the 1, up to 2 to the 4, there are 5 of them. 5. And the 5 are, those 5 divisors are 1, 2, 4, 8, 1, 2, 4, 8, and 16. 1, 2, 4, 8, and 16. Yes, 5. So the product is 15, and is indeed what we found. So that's okay. But it's not okay if I try to use, to imagine that I have a theorem saying that the function is completely multiplicative, and it's not completely multiplicative. Just like Euler function, it's not. Let's write this is not. So I need to be careful. If I want to use the theorem, I use it for numbers that are relatively prime. It's not completely. Not completely multiplicative. Now let's see an example. I would imagine, just before trying, that this would not equal, just a guess, but I'll check. If I'm wrong, I'll give another example. As soon as we find one example, the function is not completely multiplicative. Nu of 4, nu of 100, because 400 is the product of these two numbers, but they are not relatively prime. It would be a total shock, so to speak, to see that this is the equality. So I guess it's not. We actually computed this number and found that it's 15. We computed this earlier. The number of divisors, oh yeah, it cannot hold equality. We computed the number of divisors of 100. We even wrote all of them, put all of them on the board. And these are 9 of those. So I don't even need to compute the number of divisors of 4. Not that it's difficult. It's not going to be equal. I mean, this times 9 is not 15. But how many divisors we have? 3 divisors, 1, 2, and 4. So see, this is 3 times 9 is 27, it's not 15. So this is not true. So both those functions we discussed so far, from this point of view of being multiplicative or not, Euler function and the number of divisors are both multiplicative. None of them is completely multiplicative. Now let's go to the main theorem. That's the one that we use, and it's very simple, and we already discovered this. You tell me if we need to stop. You said if we put 40 minutes, stop. 40 minutes.
We can stop. We're an hour and 14. We'll stop in 5 minutes.
We'll stop in 5 minutes. Okay, good enough. Let's see. Let's write the theorem. The theorem was exactly this: that I see any prime. I don't care about what primes I have. Here, 2, 5. Only look at the exponents and add 1 to each exponent. Multiply the results, and this is the number. This is the total number of divisors. So we state it as a theorem, and as the one we use in practice. don't see it, but okay. I know what it is, and I already mentioned. We just add 1 to x. But I want to make sure that I use the same notation as in the textbook, because if someone wants to look and compare what we're doing, what's in the textbook, they can. It's easier if I use the same notation. So this would be theorem. I guess 3.8. Let n be. We look at the prime factorization. P1 to some exponent A1, P2 to A2, and so on. P, I don't know how many primes, we don't care. Say R primes to the A sub R. Okay, let's say where these are distinct prime numbers, as usual, with P1, comma, P2, comma, PR, distinct primes. And A1, okay, primes, no period there. Put a dot later. Something about the A's. These are integer numbers, non-negative integers. And A1, A2, AR, non-negative. These people with their textbooks are funny. Instead of saying, okay, this is a positive number, instead is, if it's positive or 0, they say it's non-negative. And they say it's positive if it's strictly positive. Other people say, no, what do you mean positive, strictly positive is the same thing. So that's why anytime I say I want to be very clear, non-negative in this context, numbers that are integer numbers larger than or equal to 0. But if they are allowed to be 0, why do I put them there? I'm not going to. Okay, I mean 7 to the 0 is 1, it disappears. Just because the theorem still holds, he allows himself to write it like that. It's fine. Same. This will be positive in all our applications. Just write the prime factorization and the exponents are positive. But let's see what the conclusion is. So we need to finish this with a theorem and an example. Not an example of a difficult computation, just a direct computation. We saw several examples already, or one-line example. Let's see. Then the number of divisors of n is the following product. Add 1 to the first exponent, a1 plus 1. So it's the first number, it's a sub 1. That's notation. And then plus 1, the whole thing, times a2 plus 1. And then the product. AR, and then plus 1. So, as an example, it will be pretty painful to find, or at least say, all the divisors of a number like 600. There's lots of those. What is 600? So let's see, can we do it quickly in a few seconds? Let's see, I just look at the prime factorization. 600, it's 6 times 100, it's 2 times 3 times 2 squared, 5 squared, that's 100. 2 times 3 is 6. I collect them together and I have 2 cubed times 3 to the 1 times 5 squared. It's 3 to the 1, I don't need to put the 1. That's it. 25 times 8 times 3. That's 600. Then I immediately compute. You see, I can compute this instantly. I say the number of divisors. I'm not going to write lots of them, but the total number we can immediately find. We just, as in this general formula, add 1 to each exponent, multiply the results. So it's 3 plus 1 times 1 plus 1 times because it's a 3 to the 1 in there, and then 2 plus 1. This exponent plus 1. So in other words, this is 4 times 2, 4 times 2 times 3. And this is 8 times 3, 24. Or 6 times 4, 24. It has 24 divisors, lots of divisors. Maybe it's a good time to stop this recording. You come and we're going to touch that.
All right.
All right.